Excellent. Okay, so let's get started here. We'll jump through this really quick. The first thing I always like to talk about is just who are we friends with? Who do we like to work with? CrisisMappers has been an organization we've been working with for about 3 years now. We have a number of other partners listed here, but first and foremost, we really try to do as much as we can with these different communities, with these different partners. For us, that's a very important part of what we do. And what is it that we do? Well, the first thing we do is we try to address our customers' problems. Who are our customers? They fall into a number of different industries, one of them being the defense industry, law enforcement, public safety, as well as the financial industries. So if you look at banking, if you look at financial markets, and so forth. What do all of these different industries have in common? Why do we deal with these different types of customers? Well, they all have real complex data problems, and there's something that we've really enjoyed doing over the past 12 years at Oculus. We really enjoy taking complex data problems and trying to present them in a visual fashion that people, you, me, anyone else out there, can actually make sense of the data. And so if you look at these different types of approaches that we've taken when it comes to open source intelligence, risk analysis, GIS, and so forth, we really focus on the visualization of these complex problems. Oculus is not a data processing company. We're not a database type company. We are all about how to present the underlying information to users so that they can make sense of it. Some of the things that we've done over the past while, obviously we're all here today for the CrisisMappers webinar series. We do a number of posts of different data sets that we download and do analysis on. We publish a number of research papers every year, and then we participate in a number of events. The VASTA competition is one that we do on a yearly basis, and really enjoy engaging in these different activities, because it's all, for us, it's all about getting the right kind of visualization out there. To give you an example of how we look at this stuff, I'm sure this is for some of you probably the second or third time you've seen this, but how do you look at movement data? Movement data is something that we obsess of inside this company. We're all about trying to find better ways to look at how things move and how you understand that movement. Really quickly, here are some dots on a map. Everyone's seen dots on a map, whether you're looking at Google Earth, Yahoo Maps, ESRI's ArcGIS, whatever it may be. You're always going to be looking at something that has a location. If these dots were all connected, so let's say this was an individual who'd been moving around the country, we can now draw a path of where he's gone, but we still can't really understand his movement that well. We know if he went to Washington and then Oregon, but we don't know which direction he was going. We don't know if that was in the summertime. We don't know how many times he did that. And so what we did was we came up with a novel way of looking at that, which was to add a timeline to this piece. And the timeline is going to allow us to see these events over time. So we can actually look at what we call the chronological order of events. And that way we can understand movement. We can actually see the full extent of that movement, and that's very important. We did this in a product we call GeoTime. Very, very useful for looking at stuff like GIS data, communications data, you name it. So this is for us as an example of one of the ways that Oculus works, which is trying to find a really hard data problem and solving it in a visual fashion. That's all for me. I just wanted to give you guys a quick little introduction there. I'm going to pass it over to Ali, and he's going to give you guys the main presentation of the day. So without further ado, Ali, you take it away.
So as Jen mentioned earlier, my name is Ali Asjad Naqvi. I'm currently the research director for Center for Economic Research in Pakistan. Here I will be sharing with you essentially what was my dissertation work based at the New School for Social Research in New York. So here we are basically talking about innovations, and one innovation is that we've all been part of is the crisis mapping networks, how to crowdsource data. So I'm going to talk about another innovation, which is simulations, and how they can be integrated with crowdsourced data to come up with sort of a more realistic real-time analysis. So I'll quickly take you through 3 sections, basically discuss current issues with disaster analysis, take you through the setup of a basic agent-based model. I'll show you a small video clip of a simulation. I'm sure we tested the model itself, but I think I didn't have enough bandwidth to show you the model in real time. We'll see an application of an actual disaster, the 2005 earthquake that hit Pakistan in the northern part, and then I'll just recap. So let me start. Three big issues in disaster analysis. Baseline data is really poor, especially in low-income regions. So if a disaster strikes, you really have no idea what happened, what's the pre and the post of the disaster. Secondly, credible micro-level data takes forever to collect. Some estimate that for a really methodologically consistent data, it takes about 5 years for a data set to come about, which then result in delays in policy response, which basically means you're letting things get worse before you actually implement policies. If we actually look at the models, really no proper models exist on short-term analysis, and there are three main reasons for that. One, natural disasters put economies in an out of equilibrium state, which is really, really difficult to model. Even if you are able to model them somehow, channels of causality are hard to determine because you end up in feedback loops. Everything is affecting everything else. On top of that, even if models are made, you end up with untractable parameters. You cannot isolate the impact of one parameter or another. For example, you cannot know how a population displacement is affecting price of a basic commodity in some region. So to sort of these problems, what I propose is basically you can use simulations which can, in some senses, sort out all these problems. So once we start building a model, I'd just like to start off with a very basic assumptions about a stylized low-income region. You assume a circular flow economy with spatial and temporal dimensions divided into sub-regions, which we call villages and cities. We introduce several agent categories. Let's call them low-income workers, let's call the low-income people laborers. Then we introduce landowners, business owners, etc. We also introduce basic commodities. For example, a consumable good, let's call that wheat, and some tradable good that's produced in the economy. So essentially, we are really looking at a vast majority of population which engages in subsistence farming, and as you all know, that this is the population that gets affected the worst. So we set up the model, let it run, let it stabilize, and then we can essentially do three kinds of shocks. We can do a productivity shock. What happens when you disrupt production of basic food items, especially if they are self-consumed? What happens if populations die? Because that will leads to adjustments. Also, what happens if transport networks are disrupted? For example, roads, transport vehicles, how does that affect? So the example I'm going to show you will just focus on laborers and the basic consumable good item, which we call wheat, and a productivity shock. So just to give you an overview of the framework, here we are looking at how the model is set up. So over here we have the laborers, which grow and produce wheat in villages or work for wages in cities. They migrate around, which essentially results in so basically they move around the system, resulting in migration patterns emerging. From the income they earn, they're consuming, buying goods from the market, resulting in a circular flow economy. So I won't go into the model in detail, just to give you a sense, of a small sort of semi-closed system where low-income workers can't really do much except revolve around in the system. So let me just quickly shift to the movie. Can you guys see the screen? Okay, great.
Yeah, we can, Ali. We can see the screen.
Okay, great. So let me just give you, so this is basically the model interface of a simulation model. And basically, I wanted to show you this in real time, but I ended up making a movie just in case there's an issue with the network. So the gray patches represent cities. The yellow patches represent villages. The dots basically represent agents moving around the system. What you can see is then transport vehicles moving goods around. So we are now moving away from developing a theoretical model to actually setting up a system, and here you see a bunch of graphs. So you can see a population that is relatively stable, which is the rural-urban population ratio. You can see the income distribution in villages and cities. You can see migration flows, which are almost minimum. Essentially, system is stable, which has so the system is stable, essentially resulting in stable real incomes and differences. Supply of commodities is stable, which is almost at zero, meaning that the demand is fully being met. The prices of commodities are stable. Here I make a strong assumption in the model that individual markets hold a certain amount of stock, which is more than what the total demand is, so which acts as a buffer. So turnover basically means that if suddenly the production is disrupted, this system will be able to support the populations for the next 40 days, after which the system will run out. So here I'm just going to do a very basic shock. I'm going to do a productivity shock of 50%, where I'm going to disrupt wheat production in this cluster. So it's just one cluster. And then we'll just see how all of these parameters adjust. Now this is just one very simple example of a simulation result, and you can do countless simulations on this, which I'll be happy to discuss with you later. So let me just play the movie. So if you can see the frames adjusting, you can see how the shock happened, the population migrated. What happens is that in cities, the income distribution essentially gets distributed into a bimodal distribution. The real income drops. You can see populations migrating. The system readjusts in terms of trying to internally stabilize the system. Since the shock is not big enough, the markets are able to sustain the stock levels. The graph is not visible here, but what ends up happening is the model has an endogenous adjustment parameter, where the model sees the optimal distribution required and the transport vehicle adjusts accordingly. So does the labor migration move, where populations basically don't have perfect information, but are making decisions based on algorithms and are learning from their past mistakes. So essentially, even though the results seem very simple in nature, behind this there are whole decision-making algorithms, because here we really assume that information is imperfect and people basically make decisions based on their current situation, which results in a behavior emerging at the macro level, for example, how populations move. And here we see a simple example of how a system adjusts itself and stabilizes again. You can see in terms of the trend stabilizing, you can see population graphs normalizing, you can see how real income has once again stabilized. What you see is distributions in income have emerged. So if you just compare them with how things were earlier as opposed to later, you can really see the contrast. Now this is just an example of one simulation model, and essentially this model I'll upload online, where you can actually play with the different parameters and try out different variations on your own. So coming back to the presentation, I'll just move on to how this model was adapted for an actual scenario. So we looked at a real world earthquake in northern Pakistan. The region was modeled on actual GIS location of cities, villages, population levels. The actual fault line was used, and in the model, what I did was essentially scaled the model and calibrated the model based on the limited information that was available. Unlike the previous example, the shock was based, so the earthquake that happened in the model was disrupted everything, including productivity, transportation, and agents. But what I built into the model was a distance-based algorithm. The nearer you are to a fault line, the more likely the damage is supposed to be. So if you are nearer to the fault line, on the fault line, there's a 100% probability that you are going to die. And as you move further, the probability decreases with all of these parameters. So what I started off with really was a basic elevation layer of the area of northern Pakistan. And the blue regions are essentially the valleys, while the dark brown regions are the mountains. So here we're talking about, so this is basically northern Kashmir, the Pakistan side. What I did next was overlay it with the road network, the major cities that were in that area, and the major villages that were in that area. So you can immediately notice several things, that the road network is the densest on the valleys. There's actually one city which was on the fault line. So the fault line essentially stretches along Teutonic plate. So in a lot of areas you see this being represented as an epicenter. What actually happened was that the epicenter was along the fault line. So rather than having one epicenter where you have concentric circles emerging, you had sort of an oval formation where the shock waves spread more in a horizontal fashion along this line in this direction. So coming back to the model, what I ended up doing was essentially extracting very, very simplistic information. I took the fault line, I took the location of the villages and cities, I drew a very basic road network. So this might seem a very crude version, but the road network data I have has quality information. So these are really the major roads. So once again, this was just a model which I wanted to test out on an actual earthquake scenario. And basically, two results I would like to present about the model. One is what happened with the populations, and one, what happened with the price and stocks of basic consumable items. So this region is basically subsistence farming, where 70% of the population engages in producing items for self-consumption, while very few are migrant workers, which mostly work in cities, nearby cities. So you really don't see a more developed economy than this. So what happened with the population is that you can see two diagrams here. I don't know if these are clear, but on the left-hand side you can see the population flows pre-shock. So the intensity of the line represents of how many people were moving along the road, how many people were moving on the road at that point in time. While on the right hand side you can see the post-shock outcomes, which shows you the patterns in terms of what happened after the earthquake in the simulation model. So two main results. One was there was a huge rural to urban migration. Shocked villages, which were really along this area, resulted in a huge migration flow to shocked cities. So any nearby city, so you can see that this city, which was really on the epicenter, saw a huge influx of population. On the other hand, there was a huge urban to rural migration. So there was a shift in population distribution, where populations working in shocked cities, if they were living in villages further away, moved back to the non-shocked villages. So this result essentially comes out of the simple behavioral rules programmed at the agent levels. So the result was not built in that they have to decide on how far they live, but based on their decision-making power. And this sort of resonates with what actually happened. Once again, these are very basic results I'm showing you, and this model is currently being expanded in terms of its complexity, since newer data is now available. The other interesting effect that came out was how the price and stock of the basic consumable good fluctuated. You can see here that the turnover was on average 40 days in the markets. So two things happened. One, there was a disruption in production of food items in rural areas. Populations that were producing those items also died. Populations in villages shifted to cities, multiplying the demand in cities. So as populations moved in, the stock turnover started decreasing, where it almost hit zero. And this is sort of true of the region as well, where you really don't see a huge inflow of consumable items. These are in any case. Similarly, what happened with the prices? So you can see how the price of the basic consumable item started increasing in steps. The gray line represents actual prices recorded in the model, while the red line represents the averaged out version, and you can see how the price is increasing slowly over time. And this is also true of what happened with items of food, of basic items like food grains, milk, sugar, which were really hard to find. And I was actually in that area doing field work, and the prices had almost doubled and tripled over the time period. So just to give you a quick overview, why agent-based models? One, they are really an innovative tool. You can have programmed multiple agent categories, allow these agents to interact with each other and the environment, which allows you to test the spatial element and distributions at various levels. So you're not capturing the distributions I've shown you are really what the overall model shows you, what the average is across the whole model. What you can do is really go down at the micro level, at the agent level, and start collating the information at the sub-regional level and see how the distributions are emerging over time. In my opinion, I think this is the only tool which can really look at out of equilibrium states and adjustment processes. So I don't know how many of you are familiar with economic modeling, but mainstream economic modeling really only deals with equilibrium states and really does not discuss transitions between these equilibrium states. So agent-based models can really help us explore how these out of equilibrium states emerge, especially when population distributions are changing. Some more graphs I didn't show you were basically consumption patterns of how vulnerability in terms of consumption is exacerbated as distributions shift, and this is really critical immediately after disasters when you're deciding where to send food, where to send relief. So you really need this kind of information. The cost is really low. Once you have a baseline model, the cost of setting it up in terms of time, money, and data requirements is really low. The more specifically you want to look at certain phenomena, the more you'll have to increase the complexity. So once again, the model can be expanded in multiple ways. You can increase the overall complexity of the model. You can develop certain modules more than the others. For example, I'm now working on developing a more dynamic consumption and production model just to see how different theories work out. It's really useful for policy making. If you have the baseline model right and you're able to replicate patterns and you essentially have on average an idea of how populations function, you can really test various policies. For example, whether to give displaced populations direct cash or cash for work schemes, or just give them food. And essentially that allows you to develop counterfactuals, which allows you to test how one policy can be made better than the other. This is specifically true for low-income countries, for example Pakistan, where you really don't have the kind of resources to be testing out 10 policies. You can't even go wrong with one because you really can't re-roll the programs. Another next step which I would like to take this model into is really integrated with crowdsourced data. So right now what I have is a baseline model. What I'm envisioning is at some point in time, if crowdsourcing becomes a larger phenomena, for example, a state-sponsored event where people are responding, such data can be fed into the model in real time, where the model can be calibrated and tweaked on the fly just to give us more and more accurate versions. So thank you for the presentation. Thank you for listening to the presentation. I'm just citing, two papers. One is my dissertation, and one is a paper I published 2 years ago in the United Nations Universities Environment for Human Securities Journal. I'm in the process of writing 2 more papers to further elaborate the work. So thank you very much, and I'll hand it over back to you, Jen.
Thank you very much, Ali Asjad. That was a great presentation. The question and answer period is now open, so please go ahead and type any questions you might have in the left box. While we're collecting a few questions, I have one for you, Ali Asjad. I was wondering if you could tell us a little bit more about the assumptions that you're making about the agents and how they behave, and maybe particular to the Pakistan model, which I found interesting after the crisis in Pakistan. Can you tell me a little bit about sort of the basic assumptions that are made about these agents' behavior?
Right. So I specifically did not want to go into detail, but let me just start off the assumptions, for example, of laborers, low-income workers. So what they do is their first priority is to find work. If they find work in their own village, then that's fine. If they feel that there is a higher income being paid in cities, they will migrate. So migration is really being driven by real income differences. When they have money, they have a priority of spending it first on the consumable item and then on the secondary items. For example, the tradable good I had. So once again, a very simplistic assumption. They spend a fraction of their money wealth on buying food items, which is once again calibrated from empirical data. So in this region, they were spending about 50 to 60% on purchasing food items. And then the rest was going in savings. They consume goods based on a number of units that they can consume, a certain number of units they can consume, so it's not proportional. So to how much stock they have. They also like to hold on to stocks, which will allow them to smooth out consumption. It's very common in northern Pakistan for families, households to be owning granaries, for example, in winters. So what really is interesting is how stock levels come into play, which allow them to act as a buffer. On top of that, migration decisions take place on several factors. They look at the distance to the nearest city, the income the city is offering. So basically, that's one aspect of it. If they are harvesting wheat, the wheat harvesting is based on a crop sharing basis, which is also common for northern Pakistan, where landlords give out lands to tenants, and tenants then farm them, where tenants are allowed to keep half of the produce. So anything, Jen, if you want any more specific detail, let me know. I can also send a more detailed presentation if you guys, for your review.
It'd be fascinating to see that. Can you give us some advice to someone who is not currently skilled and practiced in agent-based models, but wants to start learning doing basic things? Are there any web-based tools that folks can use to get their hands dirty and see sort of for themselves how this might work?
Yep. So there are three types of people who do. So three levels of agent-based modeling. So at the introductory level, what you can do is start off with this program called NetLogo. It's developed by Northwestern University, and they have a very active user group. It's very easy, it comes with tons of examples. The model I showed you is actually based in NetLogo. People who are comfortable with Java or Python scripting can look at Repast or Mason, and then you move on to the really hardcore agent-based model, people who do agent-based modeling, which really write their own scripts in C++ or some advanced language. And then they really do this multiple processing on which they're dumping simulations on like 10, 15 processors and getting results. So one good example is Joshua Epstein, who did a simulation of the US for the H1N1 virus. He actually had 300 million agents and a lot of information. So if you A really good book to look at is Growing Artificial.
Growing Artificial Societies?
Yes. Which has really been the core. Yes, so like Mike mentioned, the book by Railsback and Grimm is also one of, so by Epstein and Extel. So Epstein, as I mentioned, did the one that did the US simulation model. Robert Extel is currently at George Mason. He was also one of my dissertation supervisors. He is doing a lot of work in terms of the financial modeling. So then if you look at the stuff being done coming out of Santa Fe Institute, that's also a lot of simulations being done, but more focused towards financial economics. Because I think that's where the real interest lies. But I feel that there's a huge benefit from looking at how shocks are dealt with in finance and how similar concepts can be applied to economic patterns in disaster-affected areas.
Great. There's some questions coming in on the Skype window. I'll start there. Someone's asking about gathering information inside countries with censorship and trust and information issues, if that's something that you face in this work.
So there will always be trust and censorship and information issues, and that's something that we deal with all the time in Pakistan, for example. One interesting use of simulations is really how you can determine average patterns of societies by using very basic assumptions. You know that someone, if they don't have food, they will migrate. You will know that if they migrate, they will look at the decisions of their neighbors or something like that. It really depends on what you want to do and how you abstract it. And let me just move on to the second question about specific theories you base your work on. So since my dissertation was done as part of the economics program, I can give you references to the specific economic theories on which these were based on. And once again, let me tell you that the model results are coming out based on a certain set of economic theories. It would be really interesting to see how changing theories changes the results of the model. And there are some studies which have actually done that, taken different theories and seen how results change in the model. And what really makes up a good model is that if it sort of gives you stable results for various theories that you're testing. So, any other?
Okay, great.
Yep.
Yeah, sorry. I was also curious about how one might compare results between that are generated from the agent-based model with the empirical data from the same case, and how one knows the extent to which the model fits the data, or what's the way of...
So validating the model can only be done retrospectively. So if, for example, I now have flood data on Pakistan and I would like to replicate the patterns that emerge. So that's actually a very standard question in the agent-based modeling world, is that how do you validate the model? How do you determine how sensitive the parameters are? And then how will the model change if you, for example, shift a parameter, let's say consumption changed, propensity to consume change from 30% to 50%. Is the model dynamic enough to adjust to those changes? So I feel that validation of the model really has to be done retrospectively, and it's a process. It's a relatively new field. It's still being evolved, where people are discussing ways of testing parameter spaces, of comparing different models and seeing which one works best. And once again, there's a huge literature on this. So one reference I would like to make is a professor who runs a blog called Leah Tesfazian. She runs a blog called Agent-Based Computational Economics called ACE. So there they discuss these kind of things. And once again, like crisis mapping and crowdsourcing, this field has a long way to go. But I think we now have sufficient computational power to be really, thinking about running large-scale models and seeing how, the field itself can be improved.
Great. Where do you think that this is all heading? I mean, if you had to imagine how agent-based models in general might collaborate more with sort of the crowdsourced crisis mapping that's exploding in this space, and what's the best way for this interaction to take place, what would you say would be your sort of far-reaching goal or hope?
I mean, honestly, since I really presented this work to 3 different audiences: the economists, the agent-based model people, and the people who deal with natural disasters. They are all excited about this, but it's really about creating a space for this kind of work. The space does not exist. Funding is very hard to find unless you're doing some really fancy financial forecasting or looking at war patterns that emerge, where the next attack is likely to be. So I think the space for this has to be created. And personally, I have been pushing, the different little pockets that exist. For example, George Mason, where Professor Excel is based, he would like to see this work expanded. Some people at Santa Fe are interested in this, but I think it will be another 2 to 5 years before the field really becomes. Even all these tools are integrated in one, but that's where I would like to see it go, in terms of really utilizing computational power and trying to come up with this. For example, you look at the weather forecast, that's a simulation model also, That's based on really serious computing, This can also go in that direction.
I agree, and I hope sort of to bring into some of the conferences and these dialogues and collaborations more people like you that are working in this space, so it can begin sort of conversations. So if you know any colleagues or contacts that could maybe start a small working group on this issue of agent-based models inside disaster response efforts or anything like that, that might be an interesting thing to think about.
It'll be really interesting to make a pitch to the people who do simulations. For example, your colleague that I met during the conference, he was really interested in simulations, and he was like excited to know about what's happening in this field. Let me just respond to the question posted. Suggest some documentation gathering. Credibility of information, once again, it's a question that still, even the CrisisMappers forum is grappling with. How do you know that whether, post is credible or not? And it's something, where you have to, take a risk, but at least simulating something on average is better than, not knowing what's happening on average. So I think the credibility question is a larger one that goes beyond the issue of simulations or even crowdsourcing.
Great. If there are any other questions, please type them now before we wrap up. I see a couple people are typing here, so let me pause just a moment. Siggy asks, wanted to know about the theories behind the agents.
So Siggy, I'll send you my dissertation. There's a whole chapter on assumptions behind agents.
Others are asking about if there's a way to be in touch with you directly, and some are just offering some other folks interested in working groups at the Rochester Institute of Technology, Michael Long. So it looks like we're wrapping up a bit. If there's any closing remarks you want to make, I'll let you do that. And thank you very much for speaking with us today, Ali Asjad, and thanks everybody for attending the Crisis Mappers webinar series and our colleagues at Oculus Geotime. I'll let you have the last word.
Me? Or so Jen, it'll be great if we can, if you can circulate over the Crisis Mappers list and see if we can really start a working group. I would like, essentially, I would like to expand the model further, and people might have interesting ideas. If they want to look at the NetLogo code, I can just email it, and I would like to expand it into something large scale, and sort of
okay, great.
Sort of push for it.
Yeah, that sounds like a good plan. And can you send me any details that you want me to circulate on the webinar, or excuse me, on the Google group with respect to this working group?
Yeah, I'll send you an email.
Okay, great. Well, thank you, everyone. I think that wraps it up for today. We look forward to seeing you next time for the next presentation in the series. Thank you, Ali Asjad.
Thank you. Thank you, everyone, for listening. Good night.